Hello, my name is George Sammit, and this is my term project for CSE 7319. My project is based on work I performed in CSE 8340, which is a software engineering economics course. In that course, I wrote a paper that proposed managing and analyzing technical debt in terms of expected monetary value. The bullet you see here is a summary of that paper, but the gist of it is that technical debt is a decision-making problem and one that involves monetary consequences. Therefore, smart companies and smart individuals will make decisions that either maximize profit or, in this case, minimize cost. The audience of this project is the software development community at large, particularly those concerned with making and analyzing technical debt in their systems. Trust is important, so is ease of use. As you'll see, there's a bit of a chicken and egg syndrome at play here with technical debt, that being there's a cost involved in analyzing it, but we really want to focus that cost on the most important areas. This is a web-based application, and I made it a web-based application because I felt that there would be a need for people to use it directly via the web, but also for software practitioners to be able to access it programmatically. And of course, I used the EMV solution that's described in the paper. Since EMV is core to the project, I felt it appropriate to spend a minute discussing it as well as sensitivity analysis. EMV is essentially the long-running weighted average of uncertain outcomes. It's often depicted as a decision tree, which is shown here on the right. This decision tree is also core to the project, as it is the basis for all of the technical debt analysis that we do. We essentially expand the tree basically over the number of iterations and the other input that the user gives us. Sensitivity analysis helps us answer what-if questions. And basically we hold one variable constant while we vary the other variables over their expected range. A very simple example is shown here, whereby we hold z constant and vary x in the equation to see what happens, and then we hold x constant and vary z in the equation to see what happens. We'll do this with the user input technical debt variables. In this project, I chose the classic three-tier architecture as you see depicted here on the right, which is a very high-level representation or high-level view of the system. It's essentially a layered architecture where we have a user interface that accesses business services, that accesses data persistence. In this presentation, I'm going to concentrate on the business layer, and more specifically on an implicit invocation model that I implemented for running thousands of simulations for any given technical debt problem. This essentially is a sensitivity analysis where we take a technical debt problem and we run different simulations across it. And more specifically, I'm going to focus on the connector that's used in the implicit invocation model. This is the implicit invocation model that I chose as part of the proposal for this project. You'll see that we have a reactive and a proactive technical debt analyzer. Essentially, reactive means I've encountered it, what do I do? Proactive means I'm looking at my system, which technical debt should I be addressing? Those two analyzers use a sensitivity analyzer, which essentially takes the input data and says, okay, you believe that the probability of occurrence is 20%. What if it's really 15 or 10 or 5 or 30%? And it generates different requests for simulations based on that, sends those simulation parameters through an event bus, and the simulators that are able to handle it will handle it, and then return results. You see at the bottom right hand corner there's that TDM solution, and that basically is an aggregator that aggregates all of the responses for the different events, and then that sends a notification out to the user saying that we've completed your analysis, here's the results, click this link to return back to the web page. This is the alternative option as part of the proposal that I discarded, and you'll see that it essentially contains all the same components. The only difference is that this is a publish subscribe model as opposed to an event-based model. For the remainder of the project, I'm going to talk about the as-implemented architecture. Before we get into the details, I'd like to talk about 4 specific decisions. First, I'm using a MySQL database, primarily due to its high availability. I use Python to implement the expected monetary value or decision tree algorithms. At the onset of the project, I thought I'd found a library in Python to do that. It turned out that it wouldn't work, so I ended up having to write my own, but I did continue that in Python. The core business logic in the presentation layer is in Java with the Tomcat front end. And then I use RabbitMQ as the connector, and I'm going to talk about that in specific details quite a bit here in the next few slides. This slide illustrates the deployment view of the system. On the left you see that we have a Tomcat web server, and that has a Java class that implements a service that provides access to the TechDebt management system. It communicates with the TechDebt solution server via message queue. That TechDebt solution server is a Java implementation. It also uses a message queue to talk to 2 Python servers. One handles basic decision tree analysis, and the other one handles probabilistic decision tree analysis and our attempt at a Monte Carlo simulation. The TechDebt solution server uses a procedure call to talk to a MySQL database server, which is ultimately a relational database. This slide depicts the high-level architecture of the main Java server. The 2 purple boxes at the top represent external entities: the decision tree solvers, which are Python servers, and the presentation layer, which is our Tomcat web server. Both of those feed an incoming queue handler via the RabbitMQ connector. With respect to the presentation layer, it sends requests for TechDebt problems to be solved, which ultimately ends up at the simulation processor, which performs its sensitivity analysis and determines how many simulations it wants to run. The simulations are run by placing a message on an outgoing queue to the decision tree solvers. Once all the decision trees have been solved, those messages come back in, or as they're solved, not once they're all solved. As they're completed, they come back in to that same queue handler and end up at the solution aggregator. The solution aggregator basically looks in the database to see if all of the solutions have been completed. If it has, it sends a message to the user notifier, which sends the email out that you saw earlier. That you'll see shortly. You'll note that the database here is a blue box, although it does run on its own server. There is a database component within this architecture level. However, the database itself is a MySQL database that runs on its own server. This slide shows the topology of the message queue solution. On the bottom left, you'll see that there's a Java producer whose responsibility is to make requests for TechDebt simulations. To do so, it publishes requests to a topic, and that topic looks at the message and then routes it to one of the 2 queues that you see there, either the basic queue or the probabilistic queue. The basic queue is listened to by a server that essentially will take whatever values are given and run that through a decision tree analysis. The probabilistic version receives a range of values, and then we'll pick a random value within that range as it's running through the TechDebt analysis, the decision tree analysis. Now see that there's 2 managers and then there's 2 actual servers. The purpose of the manager is to pull items off of that inbound queue and place them onto a work queue. RabbitMQ has a built-in ability to dispatch messages to consumers in a round-robin manner. The purpose of the manager itself is to pull that logic in closer to the server and not leave it in the queue. And then once the servers are done running their simulations, they'll publish that response to another queue, an outbound queue, on which a Java consumer listens and aggregates all the data. I'm going to show you an example of that here in a moment. The system itself is comprised of at least 50 different classes, and I don't have time to discuss all of them, or even really a decent subset of them. So what I will do is discuss one of the more interesting ones, and this is one of the Python implementations. As you recall, Python was used to implement a decision tree algorithm. As you recall, the decision tree is composed of the squares, which are decision nodes, the circles, which are chance nodes, and the triangles, which are terminator nodes or end nodes. And of course, the branches for a decision tree are also important, and they carry information along with them. The interesting thing about this implementation is that the branches and the elements, there's a circular dependency upon them, right? And this allows you to go forward through the tree, left to right, and that's how we end up with the values at the end that we then walk backwards and collapse back down into a single decision, and that's essentially the ultimate decision, the decision whether or not to accept the technical debt or to remove it. I'm now going to demonstrate the processing that we just spoke about, and I'm going to do it using a test program. The reason being is because in real life, as you'll see when I demonstrate that, the messages come by so fast it's very difficult to see what's going on. So I'm first going to start two probabilistic servers, and then a manager, and then two of the standard servers, and then its manager. And then I'm going to dispatch 6 messages to the queue. And you'll see that each of the managers received 3, so this is the basic manager received 3 of the same messages. And then each of the the actual servers received those 3 messages. So this one received 2 and processed 2, and this one received 1. You see, received, started, and completed 1. And the same thing for a probabilistic server. So here's the manager that received the 3, and then each of the 2 servers receive their respective messages. What I'd like to do now is give you a demonstration of the product end to end. I have all of my servers running here, and as you can see, there's no traffic going through any of them. I'll go ahead and kick off a request via Postman to get the process running, and then I'll talk about it because it takes about a minute or so for it to process given the parameters here. This is the parameters of my technical debt problem, and once I send the request, I'll get a response back, essentially just a HTML page saying thank you. Watch your email for a response. And as you can see, all the servers are processing. This is on my Tomcat server, which isn't logging anything, so nothing of real interest there. This server here is a Java server that essentially takes the request from the Tomcat server, and that request goes over the message queue. So similar paradigm to what we already spoke about. And this Java server goes and it takes the user input and it determines the number of simulations it wants to run, the sensitivity analysis it wants to do, and then basically starts requesting the Python servers, the ones that actually execute the decision trees, to go ahead and start running. Of course, as those Python servers complete their work, they send a response back to the Java server. That Java server basically waits for all of the responses to come back, so it aggregates all the data, ultimately makes a decision based on the data that's received. You can see we're running pretty heavy right now. We're about 70-89% CPU. I have a maximum of 100 threads running on the servers, so they're pretty active right now. And this simulation takes about a minute or 2 to run. So I'll just pause now and I'll fast forward the recording to once the simulation completes. The message just scrolled by was the email message going out, and that ding means that we just received it. So now that I've received my message, essentially tells me what the terms of the problem were. And in this particular one, I capped it at 1,000, so I only ran a total of 1,000 simulations. That's why it finishes so quickly. And it's also interesting to note that the horizon has a lot to do with it, so the number of iterations that you're going over. So in this case, if we're doing 2-week sprints, that would be 3 2-week sprints or 6 weeks. So the longer the horizon, of course, the more difficult the problem, and that's where the tree really explodes. So for the purposes of this demonstration, it's a pretty simple and small problem. We go back in and we take a look at, here's our problem. The solution in this case is to defer the debt, i.e. not remove it. The system
And then
itself
look at
is
some
comprised of at
sensitivity
least 50 different
here,
classes.
and then at the very bottom
I don't have
is our
time to
Monte Carlo
discuss all of
simulation.
them,
Again, I ran
or even really a decent
I ran
subset
1,000
of them.
simulations,
So
and
what I
by
will
and
do
large,
is
all of
discuss
them
one of the more
came back
interesting
and said,
ones.
don't
And this is one of the
don't
Python
remove that.
implementations.
So,
As
of
you
course,
recall,
1,000
Python was
simulations
used
isn't based on the range
implement a
that we
decision
have.
tree
Isn't a
algorithm.
very large number of
As you
simulations.
recall, the decision
Ideally,
tree is
we wanna
composed
run
of the
at
squares,
least
which
an
are
order of
decision
magnitude
nodes, the circles,
more
which are chance
simulations.
nodes, and the triangles, which are terminator nodes, or end nodes.
In the end, I
And
feel the
of
changes
course,
I
the
made from the
branches for a
proposal
decision
were
tree
quite
are also
justified.
important, and they carry
The
information
system is
along
much
with them.
more efficient.
The interesting thing
Originally
about
an
this
event-based
implementation
paradigm,
is that the branches and the
the
elements,
code that would send
there's a
out the
circular
messages, the
dependency
email
upon
messages
them.
to the users,
Right, and this allows you to go forward through the tree, left to right, and that's how we end up with the values at the end that we then walk backwards
the current solution
and collapse back down into a single decision.
Actually, I believe it's more extensible than the proposal. It's quite easy to add decision tree solvers. It's quite easy to add solution generators. It remains true to its purpose. Very specifically, the presentation layer deals very specifically with presentation. The business layer has all the business logic in it, and the data layer is very concerned with just data. My three main takeaways from the project are listed here. First, I experienced firsthand architectural evolution, and I really embraced the Twin Peaks model. I really saw the benefit of that, where the architecture and the implementation kind of they drive each other and they circle around each other. It's not just here's an architecture, here's the implementation, but those two are definitely intertwined. Certain aspects of the architecture that I proposed remain faithful to the proposal. Certain aspects change, specifically the implicit invocation model changed quite a bit and ended up being a hybrid of what I had originally proposed. And that leads into the second bullet, that certain choices of components or connectors drive architecture, and vice versa. Excuse me. Specifically, Tomcat drove the use of Java. RabbitMQ had several reference architectures which I followed, one of those being task queues, the other one being topics. And ultimately, all architectures have pros and cons, and I think that's the key takeaway here, is that being able to document those and talk about those and model those are invaluable. That concludes my presentation. Thank you for your time.